what is driving me to solve things with a quantum computer? Well, I'll tell you what it is. It's synthetic formation of nitrogen at room temperature and room pressure. And who does this now? Bacteria do it. But we can't seem to harness this energy that bacteria do to do this synthetically. So why do I have nitrogen on the screen? Well, what do plants need? Nitrogen. So what's the problem, plants? Nitrogen is everywhere. Nitrogen is 70% of the atmosphere. So how come you can't get that nitrogen? Well, the nitrogen bond is a triple bond, and that's extremely hard to break down. Now, there's a molecule that has this all stripped out, and that's ammonia. The chemical formula for ammonia is nitrogen and 3 hydrogens. So somehow nature, through its magical ways, has created this ammonia type fertilizer that keeps all these plants growing. So let's see if we can unravel this. Here's nitrogen, and it is atomic number of 7, meaning it's got 7 electrons. And electrons are really important because electrons tell us whether this thing is going to combine with other elements or not. Okay, you can see it's got this 2 and this 5. These are somehow, they're reorganizing the 7 electrons in these 2 different things. And I think you'll know pretty soon, this 2 is the 1s shell. And those electrons are covered. Nothing's going to happen. But here I've got 5 electrons. So we've got 3 other energy levels to fill before this thing is complete. Okay, here's the electrons. We've got 2 of them in the 1s shell and 2 of them in the 2s shell. So these things are pretty well covered. You can see those are covered up. Now I've got these 3 2p orbitals that aren't lined up with anything. So this is what's going to make up the triple bond with hydrogen. Here's ammonia. This is what we want to create. And this is what we're going to do our computer model of. So here are the 3 electrons that fill in those 3 p orbitals that we just looked at. And this is the lone pair for the electrons that are in the 2s shell. Now if we look at all these, this forms a tetrahedral geometry. That's what this 107 degrees is. If it was a true tetrahedral, it would actually be 109, but because of the way that the forces act, these get squished together a little bit to be 107 degrees between these. Here's the Python script that generates a computer model of the atom of ammonia. Now, why are we messing with this? Because there's lots of models of ammonia that we already have. But if we learn how to do this one, then we can train the computer to do things that are much more complicated that conventional computers don't work out right, that need a quantum computer solution. So let me go through this quickly. Here's the computer script, not very long. Goes through and calculates the different properties of the ammonia atom, and it figures out what the minimum energy is at a particular bond length, which is what the big deal is. And then it also generates a plot, which is a nice thing to look at. I'm going to let my old friend ChatGPT help me out on giving some nice descriptions of these different things. So first of all, we set up the NH bond lengths. What's that all about? Well, Remember on that tetrahedral shape, we had the distance between the N and the H, and at a certain point, it's going to be the equilibrium or the low energy point. All nature tends to go towards the low energy situation. So here's some, you start at 0.8 angstroms, go up to 1.5 angstroms, and you divide it up into 8 different pieces. Now we set up the HNH bond angle. Ah, there's that 107 degrees from that picture that I showed. So that's what this line is all about. So we go down here, the quantum mapping. Well, somehow we have to map what we're doing to qubits, because after all, it's a quantum computer, so there have to be qubits involved. So the fermions, which those are the electrons, it's a fancy general term for electrons and other things that are fermions, and those get put into this mapping situation. And here's the function that it sets this mapper up ready to go later on. The results is just an array of the energies and the bond lengths. Then this is a for loop. If you know anything about Python and for loops, it keeps going around to the different radii using, they're all in this RS array that we set up with all those different bond lengths. So it's going to go around 8 times and create 8 things. Then we have to define the atoms. Here's one atom, 0, 0, R. What's that all about? Well, this is on the z-axis. You notice the x-axis is 0, the y-axis is 0, and the R is the connection between the nitrogen atom and the hydrogen atom. Now, down here, these get a little bit different. Notice the theta. Theta was that 107 degrees, 107 degrees, 107 degrees, 107 degrees. So this happens to be in the zx plane. And then these are zeros because we're not dealing with the y-axis. So we've got the z-axis, the xz plane, and the y-axis, which doesn't show up here. Anyway, it sets up the 3D coordinates. Is that understandable? Maybe not. Let's keep going, even if it isn't. Here's the molecule string that we're building, that we're going to pass to this magic function that deals with the molecule arrangements. And here's, remember we already defined these H1s, these H2s, and the H3. So those all fit together in this molecule string. Where's nitrogen? I don't know. It should be in here somewhere. Okay, down here. Here's nitrogen. Here's hydrogen. Here's hydrogen. Here's hydrogen. So those show you how the numbers are going to get spit out. Oh, there's a nitrogen up here too. I just looked right past it. Now this is going to take that molecule string that we just dreamed up here, and then it's going to apply this to the methodology for solving for the energies. And this basis is one that's crude, but it doesn't take up much computer power, which is important for what I've got here. Now, charge 0 and spin 0. The spin 0 means all the electron spin levels are matched up, which is what they are in a molecule very typically. Here we have the driver. What's the driver? Well, the driver was defined farther up here by this thing. See, we define the driver, and then once we actually run that driver down here, and that gives us the result. And then finally we take that fermion operator and we map it to a qubit. And somehow, once we get that qubit thing all designed, then we do this solver, which does all the magical values, the eigenvalue, and all those different mathematical things to come up with a result. Total energy, we have to include not only the result eigenvalue, but also the nuclear repulsion energy, because you can't forget once once the nuclei come closer together, they're going to tend to repel each other because they're a positive charge versus the electrons that are going through that. Then I've got a little thing to convert it to electron volts, and if I run this darn thing, it takes about 20 minutes to run. So either the computer program is written incorrectly, or it actually takes a lot of computations to make this whole thing work. Okay, here's my output from running this script that we looked at. And you can see it has the different radius lengths, and the winner is 1.10 angstroms. Comes in at the lowest energy level, or I should say the greatest negative level, because greatest negative is going to be less. So anyway, this is the winner, and it's put on this plot. Okay, here it is. Here's the results. If we had used a really good setup here, then this would be exactly matching this dashed red line. But with the kind of basis that we used, this is the way that it actually came out. So we said 1.1 was the minimum, which is what it shows here on the blue line. But this is actually where it should come in if we did it the right way. So using a fancier basis that took forever on a conventional computer, or at least required more RAM than my poor little machine has, then it would have worked.